Hello, this is Mr. Gummer with the 3.5 Angle Side Angle Congruence. We're going to be seeing this is our last triangle congruence for this chapter. In next chapter, we'll add a couple more, but as for now, we can achieve these three triangle congruence shortcuts in this chapter: side angle side congruence, side 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 congruence, and angle side angle congruence. Let's jump into what is the ASA congruence state. So for the angle side angle congruence theorem, it states this: if two angles and the included side of one triangle equal two angles and the included side of a second triangle, then those triangles are congruent. We're using our vocabulary word of the word included again. We saw this word included used with our included angle of the side angle side. Well, now we can apply that same vocabulary to the included side of a triangle, meaning it's the side that's formed in between two pairs of angles. So in our diagram, we'll see we've got two pairs of equal angles, and then the side that's sandwiched between those is our included side. We, of course, will not say, in our proof, will not actually refer to this as the angle side angle triangle congruence. We'll shorten it up to ASA congruence for ourselves. Here's an illustration of our congruence statement here. If we have these two triangles, ABC and RST, such that angle A and R are equal, angle C and T are equal, and the included side AC and RT are equal, then we can claim these two triangles to be congruent. We are going to prove this true. This is our next theorem. So here's our setup. Same two triangles we saw on the last slide. We're given the information about our included pair of sides, AC is equal to RT, and our two pairs of equal angles, A is equal to R and C is equal to T. So let's prove that triangle ABC and triangle RST are congruent. Now we're going to take this proof a page out of Euclid's proof, because the way he did it was absolutely ingenious. So how did Euclid prove angle side angle congruence? He did it through contradiction. He did an indirect method. Well, we can then assume, right, if we're jumping into an indirect method, we would make an assumption about the negation of our proof statement. So our proof statement is prove that triangle ABC and triangle RST are congruent. Well, we can assume then the negation of that, which means assume they're not congruent. Here's the thing about congruence, though. Since we've assumed that they're not congruent, by definition of congruent, what we're saying is that their lists are not identical. Well, we don't have to then say that all the values in their list are not identical. There only needs to be one that's not identical. So the way Euclid approaches it is very simple. Let's pick a pair of equal sides, or pick a pair of sides and assume that those pairs of sides are not equal to each other. Because if that one pair of sides is not equal, then the two triangles cannot be congruent. So it does dive into the heart of our assumption, which is they're not congruent, but all we need is one pair of sides. Let's take a look at a diagram of this. So here's our two triangles, triangle ABC and triangle RST. If we pick a pair of sides, let's say AB and RS, let's assume that those two sides are not equal to each other. Well, if AB is not equal to RS, then law of trichotomy says one of two other things has to happen. Either AB is greater than RS or AB is less than RS. Let's say, for our sake of the proof, we're going to stick with AB is greater than RS, which means we've assumed now that AB's length is longer than the length of RS. Now, if we had said the other, which is AB is less than RS, the proof of this other case would only differ in minor detail, which would mean that we can still grab that we're going to hit a contradiction with AB is greater than RS. That same contradiction will hold if we have AB is less than RS, which means we don't want to repeat the proof twice if they're only vary in minor detail. We can use our power of likewise to say, yeah, likewise, if we had assumed the other, we would have still hit a contradiction. So here's then an obvious point. We've assumed that AB is greater than RS, which means that RS really is a part of AB, right? Think about two pieces of string. If I had one piece of string longer than the other, could I cut the longer piece down to a segment or to a part that's equal to the other one? Yes, we can cut a longer piece of string down to equal a shorter. So what we're going to do on the next slide is, since we've assumed AB is greater than RS, we're going to cut AB shorter so that it's the measure of the segment we get is equal to RS. We're going to place a point Z on AB such that A to Z is equal to R and S, or equal to RS. Let's take a look at what this diagram holds. So we go back to our two triangles, ABC and RST. Now we've assumed that AB is greater than RS. It's a longer piece of string, which means we cut that piece of string down shorter so that it's equal to the same length as the other piece of string, RS. So we are given now AZ and RS are equal in length. Now, what we're going to do with this, with that new point Z marked, let's connect point Z to point C. With that new segment now connected, we actually have a pair of congruent triangles. Let's look for those. With the pair of congruent triangles, we are going to arrive to a contradiction pretty quickly. Let's take a look. See, we now have AZ as being equal to RS. We were given, though, that RT and AC are equal in length. And we were also given that the measure of angle A is equal to the measure of angle R. Now do you see that we have a pair of congruent triangles? As it turns out, triangle ACZ is congruent to RTS. So we have a pair of congruent triangles. Let me write that congruent statement down. So we have triangle ACZ is in fact congruent to triangle RTS, and that is by side angle side congruence. So what happens then if we have congruence? We can bring CPCTE to the party. We now can invoke what other information we know. Well, as it turns out, take a look what happens. There are two angles in which correspond in these two triangles, and these two angles are going to lead us to a contradiction. See, angle C in our first triangle actually corresponds with angle T. What we're really saying is that there is this angle here. Now, I'm going to be very careful how I mark it. Notice that I'm marking only just that angle there, right? There's this kind of little smidge that is left over, right? There's that little smidge. We can claim that that angle ACZ, this angle that I've marked here, is equal to angle T. Well, okay, so let me make a note of that. So we've claimed that angle ACZ is equal to the measure of angle T. Well, we already know something about the measure of angle T. Angle T is equal to the entire measure of angle C. That's given. Okay, so now what we can then say by transitivity equality is that the measure of angle ACZ is equal to the entire measure of angle C. So what we're claiming is that this small part is equal to the whole angle. That's what we're claiming right here. Well, that can't be. We've claimed now that the whole is equal to the part. That is never true. We proved that the whole is greater than the part, which means this right here is our contradiction. We assumed that AB and RS were not equal to each other. We assumed that AB is now greater than RS. Now, if I had assumed that AB was less than RS, you would see that, hey, we would arrive to the exact same contradiction, where we would claim the whole is equal to the part, and that can't be true. The whole is always greater than the part. So now, since AB cannot be less than RS and AB cannot be greater than RS, we have a contradiction with either of those two conclusions. So what is our conclusion now? Our conclusion, since we assume that AB is not equal to RS, that's wrong. We have to then toss that assumption out, and we can conclude that AB has to be equal to RS. So what does that do for us? Well, what that does for us now is we have now enough information to claim that these two triangles are in fact congruent. How? By side angle side congruence. Because AB, by our conclusion that AB and RS are equal, we now have an equal pair of sides from AC and RT, a second pair of equal sides from our indirect method of showing AB and RS are not equal, which means they have to be equal, and we're given that angle R and angle A are equal, which means we do have side angle side between those two triangles. So thus, we have a pair of congruent triangles. Now we've added a new triangle congruence into the mix. We have side angle side, side side side, and now angle side angle too. Now, to end our lesson, let's actually use angle side angle in a proof and actually take a look at, are there other triangle congruences that we have not considered? And we're going to take a look at what are some other possibilities that we have not considered. So in our last several slides, let's actually use angle side angle in this proof, and then we'll move on to finish of their other triangle congruences. In our proof here, prove that if a segment that bisects an angle of a triangle is perpendicular to an opposite side, then that triangle has to be isosceles. Well, what we need is a diagram first. All right, so I have this segment that is going to bisect an angle, and is perpendicular to the opposite side. Let's call this triangle ABC. This segment we'll call AD. So AD cuts the top angle in half, right? Angle BAC, bisects that angle, and is perpendicular to the opposite side. Let's prove that this triangle is isosceles. In order to show the triangle is isosceles, we need to show that there is a pair of sides that are equal to each other. Well, in this case, I can prove that AB and AC are equal to each other. Let's get there. So we're given, all right, so this is what we're given. We're given that AD bisects angle BAC, and we're given that AD is perpendicular to BC. Okay, AD is perpendicular to BC, and AD also bisects that top angle, angle BAC. All right, we're going to prove that AB is equal to AC, and I'll do this paragraph style. So given AD bisects angle BAC, then the measure of angle BAD is equal to the measure of angle CAD. Okay, that is by our definition of angle bisector. Okay, so I have an equal pair of angles. What else do I have? Well, I can claim then that angle, oh, I should say this, also given that AD is perpendicular to BC, then I know that angle ADC and angle ADB are right by the perpendicular lines theorem, right? We proved that if the two lines are perpendicular, it forms four right angles. Well, I can claim all angles formed at the intersection then are right angles, which then means I can claim that the measure of angle BDA is equal to the measure of angle CDA. And that really, that's kind of using several theorems, right? There are several things. That's by the definition of right, because they're right angles, and transitivity of equality, right? We can prove that both of them are 90-degree angles, and then they're equal to each other, which means, yes, I have another pair of equal angles. Lastly, with common side AD, right? Look at our common side AD. I can claim, so with common side AD, I can claim triangle ABD is in fact congruent to triangle ACD by angle side angle. So then I can invoke by CP CTE AB is equal to AC, right? AB is equal to AC. Moreover, triangle ABC is isosceles. QED. There we have it. All right, proving that a triangle is isosceles. Now, of course, you could have done this column style. Either way, paragraph column style, we're going to arrive to that same conclusion. Now, to end our lesson, let's talk about, are there other triangle congruences out there? I should say other triangle congruent shortcuts, right? Because our magic number is 3. So now, yes, there's a little giggle on the next slide. You can giggle on this next slide. What about angle side side? Uh-oh, Mr. Gummo, there's a big bad word at the top of your slide. No, so here, let's talk about this. So we have side angle side, we have side side side, we have angle side angle. Are there other angle and side combinations that we can make such that we have congruent triangles? Well, in chapter 4, we're going to find that angle side, yes, is another theorem to prove that triangles are congruent. But what about angle side side, thus the title of the slide? What about this one, angle side side? Well, we should not consider angle side side as a triangle congruence principle, not just because it looks like a bad word, but because it has counterexamples to it. Consider the diagram below. We actually have two triangles here that follow this angle side side pattern. Let me point out those two triangles. Consider the first triangle, ADB. It's this one right here. Let me change my color real quick so I can actually juxtapose these two triangles with each other. So let's then also consider triangle CDB. Those two triangles, if we were to claim them as angle side side congruent, they would not be congruent. This is actually a quick counterexample. Let's take a look. First of all, the two triangles share an angle right here, angle D. which means, yes, they have a pair of equal angles. They also share a pair of equal sides right here. They share BD, which means there's our angle, there's our side, and then as you take a look, we were given that there was a pair of equal sides already there. So that would be angle, side, side, angle, side, side. Well, those two triangles are not congruent by angle, side, side, obviously, which because of the counterexample, we cannot claim angle, side, side as a valid triangle congruence principle. Okay, so just be careful with that, right? Noting that angle, side, side, not every combination of angles and sides works. There's another combination of angles and sides we haven't considered. What about angle, angle, angle? If the three angles of one triangle go three angles of another, does that mean that there's congruence? Not necessarily, right? Take a look at our example here. I could have a side of 3 and a side of 7 here. Do all three angles of the first equal all three angles of the second? Yes, but are their sides equal? No, which means I'm not proving congruence. Here's a quick counterexample. There is something that angle, angle, angle does prove, and that's not in this chapter. We're actually find that way later in chapter 7. There's going to be some information about what it means for these two triangles here. They're not congruent, but they are something else, a little bit of foreshadowing for ourselves. So to end, let's take a look at our congruence scorecard, right? We've actually considered all 6 of the different combinations we can make of angles and sides. So we have side, angle, side. We have side, 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 and angle, side, angle. Those are the 3 that we've talked about so far. In chapter 4, yes, we will prove angle, angle, side. We don't have the necessary tools to get to that just yet, but when we do get those tools, yes, we will prove that angle, angle, side is a true triangle congruence principle. And then, of course, angle, side, side, and angle, 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 we have to mark those off. Those are not triangle congruence. There's no other combination we can make. There's some variations, but they'll also fit into one of these 6. So there's no other combination we can make to actually prove triangle congruence. There actually is one other case that we'll see in chapter 4 of our 5th triangle congruence, but it's a special case, or it's a very special case that happens to prove that the set of triangles are in fact congruent. All right, we've come to the end of our lesson 3.5. Be sure to work on that worksheet with the angle, side, angle congruence now in play. If you do have any questions on that worksheet, do not hesitate to email me. With that, be good and do good.